Hello everyone, my name is Christina Ovezik and I'm a PhD student at the University of Edinburgh. Today I'm going to present this joint work with Dimitris Karakostas and my supervisor Aggelos Kiayias on the topic of blockchain decentralization. So first of all, why is it interesting to study this? Why is blockchain decentralization important? Well, the advent of Bitcoin and other blockchains brought forward a lot of discussions about decentralization. But while these systems have a lot of potential, in practice, their levels of decentralization are highly disputed. And while blockchain decentralization is often on the news, there are many different and often contradictory reports about it. Decentralization also serves as a deciding factor for users and organizations interacting with blockchains, and is also relevant in several regulatory discussions, such as the question of whether to classify digital assets as securities. Blockchain decentralization has also been a topic of interest in academia for at least a decade now, and there is a growing body of research work dedicated to it. Again, both positive and negative results have been presented from both empirical and theoretical perspectives. Oftentimes, decentralization is reduced to some particular aspect of blockchains, with different works focusing on different parts of the system. So we've seen that decentralization is a major talking point from many different perspectives in academia and beyond. But let's take a step back. When we talk about decentralization, it's typically in the context of permissionless distributed systems. In this kind of systems, anyone can participate and they can join or leave at any time. Often, this definition is seen as synonymous to decentralization. However, just because anyone is allowed to join the systems doesn't mean that people will actually join the system and participate. When the permissionless system does not attract enough participants, it's hard for it to be considered decentralized. But even if a lot of people do join the system, economies of scale may incentivize them to pool their resources together. This is what happens, for example, in the case of mining pools, where miners come together under the same organization, which can offer them a more stable income, but can also be detrimental to decentralization. So let's suppose that for one of these two reasons, either lack of sufficient participation or because of economies of scale, we end up with a system that's not decentralized, with a blockchain that doesn't have decentralization. The question is this a problem? And if yes, why is it a problem, especially from a cybersecurity perspective? Well, the answer becomes pretty clear when we start thinking about single points of failure. The concentration of power into few entities can threaten the security of the system if some of these entities become compromised. Single points of failure can lead to catastrophic system failures, like the explosion of the Death Star we see in the comic strip, but it is also critical to explore single points of failure in the context of any desirable system property. For example, in the case of blockchains, we can say that a single point of failure might be something that has the power to violate the ledger's safety or liveness properties. Therefore, from a security perspective, we can view decentralization as the distance from these single points of failure. Now that I have hopefully convinced you that blockchain decentralization is important, we can move on to the framework that we propose in our paper. We reviewed more than 100 papers on the topic, and it became pretty clear from the literature that blockchains are multi-layered systems with each layer contributing to the decentralization of the system as a whole. In particular, we identify 8 layers relevant to blockchain decentralization, and we remark that centralization in some layer can compromise desirable properties of blockchain systems, such as safety, liveness, privacy, or price stability. So for each layer, we ask 3 questions. First, what is the resource, or what is the unit of interest in that layer? Second, which are the relevant parties that either directly or indirectly control this resource? And third, which properties are at risk if this distribution of resources to relevant parties becomes centralized? So let's have a first look at the 8 layers I talked about. We can see that they range all the way from hardware up to the governance layer, and with geography touching upon all other layers. In the diagram here, we can see some examples of resources and relevant parties, and how within such a distribution there can be entities that control multiple resources, like the orange person in the top row controlling multiple tokens, but there can also be multiple parties who have joint ownership of a resource, like the case of the blue person and the red person, who both have control over the same token. We also propose a practical test called the minimum decentralization test, or MDT, that can be particularly useful from a legal perspective. A blockchain system fails this minimum decentralization test if for some layer there exists a single legal entity that controls sufficient resources to violate a property of interest. We can imagine, for example, that if a single organization is responsible for taking all the decisions in some system, then that system would fail the MDT, in particular because of the governance layer in this case. Note that we call this minimum decentralization test because we have the minimum requirement for one legal entity. But this can easily be generalized to a k-entity version. Now we can take a deeper dive into the 8 layers that we have. For each layer, we'll have a slide that looks pretty much like this one, where I will outline any sublayers that might exist, as well as the resources and relevant parties that we identified for each of them. In the interest of time, I won't go over the affected properties, but you'll be able to see them on the slides, and of course you can find details for all of them in the paper. I will also present some evaluations of Bitcoin's decentralization with respect to each layer based on academic and industry reports, or at least some approximations of them when the relevant data was not immediately available. So the first layer we're going to look at is the hardware layer. We distinguish between 2 different categories of hardware, namely physical hardware, that is the equipment used directly by protocol participants, and virtual hardware that can be rented through hosting providers. In both cases, the resource we're looking at is participation power, which, for example, can be computational power or stake, and then we'll look how this is distributed across different hardware manufacturers or hosting providers. In the case of Bitcoin, there are 4 companies, 4 ASIC manufacturers that dominate the mining hardware market. The second layer we have is the software layer, which is also segmented into 2 sublayers. First, we have protocol participation, which is concerned with the software that's used to run full nodes and participate in the protocol. In this case, the resources are the participating power, but also the number of full nodes. And the relevant parties are the different software implementations, as well as the developers behind them. The second category is asset management, which is about wallet software, which is responsible for address and key management. Here, the resources are the tokens that are hosted in these wallets, and the relevant parties are the different wallet implementations and their developers. In Bitcoin, the vast majority of full nodes run some version of Bitcoin Core, but this is a software product that is maintained by more than 300 developers. Third, we have the network layer. Here, the first category is peer discovery, which refers to the process of initially connecting to the network and catching up with it. The resources here are the nodes that the client can use to bootstrap the network, and the relevant parties are the operators of these nodes. The second category we have is about the eventual topology of this network. The network of nodes is typically made up of several components, where a component corresponds to a single node or a group of tightly connected nodes. Then there are some nodes that sit in between these different components, and they practically control the flow of information between different parts of the network. And these are the nodes we care about. We call them component bridges here. So these are the resources here, the nodes that control the flow of information in the system, and the relevant parties are the owners of these nodes. The majority of nodes in Bitcoin operate over Tor, which makes it rather hard to analyze the topology of a network. It is estimated, though, that the nodes are evenly spread across multiple autonomous systems. The fourth layer we have is about the consensus or a block production mechanism of a system. Notably, this is the layer that most people focus on in the context of blockchain decentralization. Here, we want to look at the distribution of participating power, such as computational power or stake, across the parties that control it. There are cases where the entities that exercise control over the resources are not necessarily the owners of the participating power, but they have received it as some form of delegation. This is the case of pool leaders, for example, who are given the power, among other things, to choose a block's content using the participating power of pool members. Mining power in Bitcoin is distributed across thousands of machines, but there are a handful of mining pools that collectively control more than 3/4 of it. The fifth layer we have is about cryptocurrency economics or tokenomics. One category here is about the initial distribution of tokens, meaning the way that the tokens are allocated during the launch of the system. Then we look at the token ownership after the system has matured. The resources here are again the tokens, and the relevant parties are the key managers and the legal stakeholders of those tokens. Note that we make this distinction because these can be separate entities, for example, in the case of custodians. Last, we also look at secondary markets, where we are interested in the liquidity of the asset across different trading pairs and across exchanges. In the case of Bitcoin, there are more than 40 billion addresses that own some amount of tokens, with the top 100 of them controlling 14% of all wealth. Bitcoin trading takes place on more than 100 exchanges with very high volumes. The sixth layer is the client API, which abstracts the way that applications interact with the blockchain. In many cases, applications such as wallets use trusted intermediaries to access basic blockchain functionality. This is typically done to improve user experience, as people want fast access to their wallets and they don't want to wait for the full node to sync. In this case, the resources are the tokens that are hosted on these applications, and the relevant parties are the full node operators that provide them with a view of the blockchain. There are more than 70 such wallet applications for Bitcoin that use intermediaries to validate the state of the blockchain. The seventh layer we have is about governance, which we segment into two categories again. The first one is about improvement proposals and conflict resolution, where we look at the distribution of decision-making power across all system entities. The second category concerns research and development funding. So the resource in that case is capital, and the relevant parties are the developers that get funded for their work in the ecosystem. In Bitcoin, it has been shown that there are only a handful of users actively contributing to Bitcoin improvement proposals, but there are hundreds of companies operating in the wider Bitcoin ecosystem. Last, the eighth layer we have is geography, where we distinguish between the physical safety and the legal compliance of the system. Geographical decentralization can manifest in many forms, interacting with practically all layers and resources that we have described so far. For example, we have talked about the distribution of tokens to stakeholders, but then there is a question of where these stakeholders are located and under what jurisdiction they fall into. And we can say the same about full nodes, participating power, and so on. In the case of Bitcoin, there are nodes present in 95 different countries, but more than 1/3 of the mining appears to come from the US. To sum up, our systematization identifies 8 layers of blockchain decentralization. Each layer is described by one or more resources and the sets of relevant parties that control these resources. Concentration of a layer's resource into the hands of few parties threatens desirable system properties such as safety, liveness, privacy, or price stability. I also want to mention that we're already working on identifying appropriate metrics for each layer and developing tools to measure blockchain decentralization across layers. This is done as part of the Edinburgh Decentralization Index project, whose goal is to define and measure blockchain decentralization. If you scan this QR code, it should take you to the website of the ETI, of the Edinburgh Decentralization Index, where you can find many of our resources and more information about what we do. And for example, you can find there our GitHub repository about decentralization on the consensus layer and a blog post that explains how to use this tool. We think this should be a community-wide effort, and we welcome contributions of all sorts. Thank you very much for your attention.